Okay, so we're going to talk a little bit about the properties of metals. And the easiest way to talk about the properties of metals is to contrast them with the properties of ionic compounds or salts. So remember, we've already talked about ionic compounds. Ionic compounds, this is a little model. They're alternating cation, anion, cation, anion. They're locked in their little prison. They're really, really hard materials. They're hard to melt. Okay? They're surrounded by opposite charges. Okay? And if you try to bend them, if you try to shift them, they don't want to shift until you finally do and you get them next to repulsive ions and they push apart. It shatters. It all just falls apart. I should do that faster. It just all shatters. Okay, so ionic compounds are great while they last. Here's an example of an ionic compound, sodium chloride. It's the same sodium chloride that you find in salt. Well, this is iodized, but other than that, the rest of it, this is sodium chloride right there. But here we have tiny little microscopic crystals. Okay, tiny little microscopic crystals. So that is salt, but this is a big crystal, a macroscopic crystal of salt. Notice how it's very square, right? Just like this was before I smashed it. Another way to represent this is with this one. I'm not as fond of this model because it makes it look like they're covalent bonds, but you can sort of see how that ion in the middle is trapped in place. It's pegged in on every single side by opposite charges. So they can't really move at all. It can't really budge. It can't shift very much, okay? So that's what ionic compounds are like, okay? They are hard but brittle. They form electrolytes in solution. Here's a little beaker of water, and I'm going to pour some salt into there. Ooh, a whole lot. I'm going to stir it up. And now this should be an excellent conductor of electricity. Wow, really bright. Even a little bit of green, if you can you see the green on there? Even a little bit of green is lighting. Okay, so that's ionic compounds. So how does that compare to metals? Okay, well, metals are shiny and metallic. So think of coins, right? Think of things that we cook with, right, on the stove. Metals, right? Why do we cook with them on the stove? Because they're thermal conductors. Look down here. Thermal conductors. This is a really good thermal conductor, right? And then they're durable. They hold together sometimes, right? But why is that? That's because of the metallic bonds. So remember, metallic bonds, the bonds in a metal, are different than the bonds in an ionic compound. They're not quite as picky, let's say. So with the three kinds of bonds, now the ionic bonds is what we have here. Okay, ionic bonds in sodium chloride or any salt, right? And then covalent bonds we've talked about. Covalent bonds like in a water molecule. Well, a water molecule, basically each one of these water molecules, they do attract each other. There's a delta positive, delta negative. This has a delta positive, delta negative. So they do kind of want to stick together. And that's actually what you get in an ice cube. Here's an ice cube. Oh, these are Darth Vader shaped, but they're still ice cubes. So inside that that one's not so good. Inside those Darth Vaders, you've got water molecules that are really, really stuck together, but the connection between them in an ice cube is actually very tenuous. That's called a hydrogen bond. What's happening between these? Because hydrogen often makes it. And that's nothing like the other kinds of bonds. That is nothing like the bond inside the water molecule. These polar covalent bonds, the covalent bonds in a water molecule, okay, there's a water molecule. It's just a little intermolecular attraction between them. So hydrogen bonds, are they really bonds? Well, not like the other ones are. They're on a totally lower level. They're down several orders of magnitude from covalent bonds, ionic bonds, even from metallic bonds. So hydrogen bonds, I don't like to really think of as actual bonds. But that is what connects water molecules, and it makes a beautiful, beautiful structure in an ice cube. The structure in an ice cube, surprisingly, is very much like the structure in a diamond. Here's an ice cube. This is inside, showing the hydrogen bonds as that little blue part. And here is in a diamond. Now diamonds, it's kind of tricky to show enough of it that you can see the structure. Here's a little model of a diamond. This is a little section of the diamond, okay? These are all covalent bonds, okay? So there's a certain way of looking at a diamond and thinking of it. If you look at it from above, it's a lot like the structure in an ice cube. Now this doesn't show it correctly because this is all flat. Obviously it's three-dimensional inside an ice cube. But the structure of a diamond and the structure of an ice cube are actually a very similar structure, except that all the ones in the diamond are covalent, and a lot of the ones in an ice cube between the water molecules are just hydrogen bonds, okay? And what's one of the reasons this is already melting? Look how he's spinning there. He's melting and floating around in his own melt water. Okay, I guess that's a sad fate for a Sith Lord. But anyway, that's because these connections are kind of easy to break. These are not, but these are, the hydrogen bonds, okay? Even easier to break, or what about with carbon dioxide? Carbon dioxide, they don't even have any polarity, even though every single one of the bonds is polar. These polar bonds are going that way, these polar bonds are going that way. It just cancels out, so the whole molecule is nonpolar. That means that they will just barely attract each other. They have a very slight attraction between each other to hold together, which is why dry ice very quickly separates and forms into a gas, which is when they're basically bouncing apart. Water molecules try their best to hold together as much as they can. Of course, they're not really this organized in a liquid. They get very organized in 3 dimensions as an ice cube, but then when they melt, they're sort of flowing past each other like this. And when they're a gas, they're bouncing apart. Okay, so water tries to avoid being a gas. It tries to hold together, but it can only do it for so long. As you can see right here, it's melting. So that is ionic bonds and covalent bonds we're talking about. Also, here's methane, that really cool 4-sided die shape, that tetrahedral shape of methane. Really cool looking molecule, right? Really cool. And that's a good one for understanding Vesper form. And then, of course, carbon can also make like a honeycomb pattern. I like to think of this as like a honeycomb. Won't you be my baby? Won't you honeycomb? Be my, right, Ian? Are you my honeycomb? Okay. And then graphite, of course, is your regular everyday carbon. Most carbon you find every day lying around, like you think of carbon as graphite. But diamond, okay, of course, is way harder. Graphite, super flimsy and soft because these layers just barely attach to each other. They can peel off like on a pencil, whereas a diamond, on the other hand, is really stuck together. And I believe we have a diamond right here. This one I calculated has 1 times 10 to the 21st atoms, 1 sextillion atoms. A little diamond, I stuck it on a piece of tape so I wouldn't drop it, because it's a very small diamond. That little diamond there has this covalent structure. Now this is kind of cool, because the covalent structure in a diamond is kind of like reminiscent of what you find in an ionic compound. In an ionic compound, you got bonds going every direction, right? Locking things into place, right? But those are just flimsy ionic bonds. In a diamond, what you have is covalent bonds doing that in every direction, locking things in place. So look at this one. This one's pegged in place with force surrounding. And so with this one, if you kept going, yeah, it's locked in place with force surrounding. This one would be if you kept going. The diamond just keeps going and going until you get to the surface. So diamond is the hardest naturally occurring material. Okay, that's a little diamond, uncut diamond. So it'll scratch anything else. Let's see, what kind of scratch? Let me scratch this piece of metal with a diamond. Should be able to scratch it, make a little scratch in it. Yep, look at those scratches, right? Diamond will cut anything else. It'll of course cut an ice cube, as you'd imagine, but it'll cut through any, let me cut this ionic compound, let me put a scratch in it. Put a scratch, see that scratch? Diamond will cut any other material because of its hardness. Diamond will even cut through quartz, which is what a lot of rocks are made of that make up the crust of the earth. Really known for being a very hard material. Let's see if we can see this. You hear that? Mm-hmm. I made some scrapes right there. Do you see them? Let's see, I'll go this way. Okay, you see those scrapes? It made a scrape in the quartz. Yeah, you can see that, right? Yeah. Okay, so diamond will cut through quartz, which is like a really hard rock. It'll cut through ionic compound. So diamond, it's kind of funny. It's like a molecule. It's a huge molecule. So big, by the way. Can't you see that? Can't you see that, Ian? That means it's a macroscopic molecule. Diamonds theoretically have no upper limit. Because of their really strong structure, they could actually get big, like the size of a moon or a planet, right? And the only thing about diamond, their dirty secret, is that the surface is always got something else on it. Most of the diamond is carbon, like 99.999%, but the very surface is always dirty. That's diamond's dirty little secret. Okay, so that's a diamond. And then there's the buckyball. We'll have this buckyball, just so you can see that it's ball-shaped, surrounding this unicorn ball. A buckyball is even harder than diamond. It's a very, very small microscopic molecule with only 60 carbons, arranged like a soccer ball. Notice this is a pentagon, this is a hexagon, this is a hexagon, pentagons and hexagons, making kind of a geodesic structure, which is why it was named after Buckminster Fuller. Okay, it's a buckyball. And look at that. Okay, this is a model of the molecule, but you can see it's really, really well held together. And whereas diamond only has single bonds, this has single bonds and double bonds. So isn't that harder? Isn't that harder than diamond? And the answer is yes. So if you could fire these little microscopic buckyballs at that diamond, it would do some damage. That's one of the only things that'll damage a diamond. I mean, you can cut a diamond with a laser and other things, but it's one of the only things that's harder than a diamond, is a buckyball. So a buckyball is just like a soccer ball. Here's a soccer ball, or here's two soccer balls. This one's kind of dirty, let's get rid of that one. Okay, so notice that on a soccer ball, you got a pentagon. See, that's a pentagon right there, that's a pentagon. Surrounded by hexagon, 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 hexagon. The hexagons surround the pentagons. The pentagons are isolated, they don't connect with each other. There's another pentagon, and then there's another pentagon, see? Surrounded by hexagons. So that's exactly what you see with the buckyball, right? There's a pentagon surrounded by hexagons, and then there's another pentagon separated, surrounded by hexagons. So it's the same structure as a soccer ball. Isn't that cool? And this is the hardest known molecule. Can you believe that, Ian?
Oh my God.
But it's microscopic because it's only got 60 carbons. Okay? So now, let's look at metals. Now, as you know, metals, okay, are malleable. You can make them into sheets like this, right? And you can roll them up. They're deformable. You can make them into wires. Okay, they're ductile. That's why they have these properties. They have these properties because of the metallic bond. These are the properties of the metal. So this is, look at this little model. This is a really good model of a metallic bond. So imagine that the metal atoms are kind of all stuck together, and it's not because they all really want each other's electrons. It's just because nobody's able to steal them. Nobody's pulling more than anybody else. So watch what happens. If I take a metal and if I try to, let's get a hammer. If I take a metal and if I try to hammer it flat, here's baby Milner again. Let me hammer it. Boom, 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 flat, right? That's how you make a metal flat, by hammering it. And notice it doesn't really matter to them that they have a different arrangement. That wouldn't work so well with an ionic compound, would it? Because then you'd be putting like charges next to each other. But metals, they're all the same, so it doesn't really matter, right? So notice how I just hammered that into a sheet. This is sort of a model of what you do on a microscopic level when you hammer it into a sheet like this. Okay, of course that would take a lot more effort. Okay, what about this? Watch. Can I make that into a wire? Well, watch. If they all hold together, why not? Why can't I make the metal pull it into a wire, right? So you can see me here pulling it into a wire. That's why this is a very good model of metallic bonds, because they want to hold together regardless of the orientation. So that's why metals are very, they have high deformation, like you can make them into all these different shapes, fold them around, okay? It's because it doesn't really matter to them which exact atom they're next to. It can shift around and it holds together, okay, giving it a lot of flexibility, right? A lot of macroscopic flexibility. And we make a lot of coins out of it. Here's an Australian coin with a kangaroo's pouch. Okay, and here's one. This is funny. I just noticed this. Here's JFK on the $50, which, by the way, they made the year after he died. He died in '63. He was already on the $50 in '64. Took a little longer to get Lincoln on the coin for some reason. But then look at this. What is this? Edward VI. Look how similar they look on here. Kennedy and Edward VI. What? Was he like our king? I don't know. I'm an anti-monarchist, so I don't think so. Anyway. So, that's one way to understand metallic bonds. And here's a smaller model. Can you see this one? Here's a smaller model. So let's say this is a chunk of metal, but I want to hammer it into a sheet. I want to flatten it out. See how I flattened this out into a sheet? And then can I roll that into something? And can I pull it into a wire, right? See how that works? You can pull it into a wire. This is a very good model. I like these little, are these called specks, Ian? Specks, right? I can really model metallic bonds with these specks. And I even have a small one representing copper. Let's see if you can see me pulling copper into a wire, because copper will hold together even when it's just a few atoms thick. Okay, so will gold, and so will a lot of other metals, because of the way the metallic bond works. So that's like a wire. Imagine this is like a wire of copper. Imagine the atoms. Now, a real wire of copper would be many, many atoms thick. Okay, it's very tricky to get one that's one atom thick. Then the slightest thing is going to break it. That is one way of comparing the three kinds of bonds that we're talking about in chemistry. And again, I guess hydrogen bonds are also a kind of a bond, but not really in the same league as these guys. These are the heavy hitters. Okay, say bye-bye.
Bye.